All right, so this is Math372, Lecture 13B, Complex Analysis. Because we have an exam coming up, what I'm going to do is I'm going to turn today into a problem-solving class, just discussing things. If you want to leave, I will not be insulted. And then I will post the link to the video from 2015. So all we really did in that lecture was just show that there is a way to define the complex logarithm, that it agrees with 1 over z, that if you integrate along the real line, you get exactly what you would expect. And so this is a good lecture to switch with just going over problems. So are there any problems people would particularly like to discuss, either from the homework or in general? Anything that seemed challenging from the homework or gave you some pause initially?
Parts the 17A.
Okay.
The question you labeled as hard.
Okay. So to be fair, I have actually not looked at the solution keys in over a year. So I have no idea, well, actually I guess 2 years. 17A. All right, so let me just see what the statement is. Oh, this is in the book, right? All right, what page is this? Page 103 maybe?
Yes, 106.
106. Okay. So, okay, screen smooth. Page 103. And this was 17A.
Yeah.
So F is non-constant, holomorphic, in an open set that contains the closed unit disk. So I'll just put that to mean the closed unit disk. All right. Show the absolute value of f of z equals 1 when the absolute value of z equals 1. Oh, so if this is true, then the image of f contains the unit disk. And the hint is show f of z equals w naught has a solution for all w in the unit disk. And the claim, it's enough to show f of z equals 0 has a root, and then use maximum modulus principle. All right, so this problem seems to be reviewing almost all the concepts we did in the big consequences to the argument theorem. We've got images of open sets, okay. We have probably, whose theorem? As soon as you see something like this? Rouchet. So it's easy at times to hide when you need to use Rouchet, but as soon as they talk about show something has a root, show something has a solution, Rouchet should be screaming at you. Okay? In other problems, it may not be clear that Rouchet is a good way to go. It's a great theorem. But as soon as they start talking about something like this, all right, and then the next is then use the maximum modulus principle. So does the function have to be identically 1 in absolute value on the boundary? So it says show if the absolute value of z equals 1 whenever z equals 1.
Oh, you mean
in modulus, in magnitude.
Yeah.
What do you think might be true about this function? So we're telling you that it's always equal to 1 in absolute value on the boundary of the unit disk. What might you think this function is?
I mean, just like an example of a function that could be.
Yeah, give an example of.
It could be z.
It could be z. What else could it be? Z squared.
Z to the n.
Z to the n. Maybe even z to the 3/2 with that, or would we have to then worry about how you take a 3/2 root? But maybe z to the n for some integer n. Do you think it could be anything else?
It could be any like z plus z squared plus z cubed and divided by the number of terms.
So this is really good. So first, it could be z squared, z to the n. Then your next guess was maybe z plus z squared over. So would that work? Because it's got to be of absolute value 1. You could have cancellation in sign. So unfortunately, you could have cancellation in sign because of something like that. So this does not work. We do not necessarily need to know this to solve the problem. I'm not stalling for time, I promise. It's just, let's use this as a springboard. When you see something like this, one of your first thoughts should be, let's classify the space of examples. Or let's look at the examples and see, if we could prove that the only things that work are like this, that would be nice. So can you think of anything else that would work? That would have magnitude 1? I can't think of anything else right now off the top of my head. And so I'm a little bit worried if we had something other than a pure power of z, would it still be able to be always 1 in absolute value on the boundary? Right? So again, we don't necessarily need to prove this, but it's good to know. All right, so let's try to use Rouché's theorem. So the first thing is, do we think there's a solution to f of z equals 0? So what are your thoughts? How would you attack something like this?
So if f of z is not equal to 0 everywhere in the unit disk,
Okay.
then we can consider 1 over f
Good.
of z.
So if f of z does not equal 0 for z in disk, we study g of z equals 1 over f of z. And that's using this hint over here, the maximum modulus. So the maximum modulus is the largest value the function can take is on the boundary. And it's stronger than that. It can't equal that value in the interior. And of course, when I'm talking about largest value, I mean largest absolute value. So the function must vanish somewhere inside. If it doesn't, I can study g of z equals 1 over f. And what do we know about g of z? Oh, and that was the good piece of chalk. So we know the absolute value of g of z equals 1 if the absolute value of z equals 1. If the absolute value of g equals 1 if z equals 1, by maximum modulus, g is strictly less than 1 inside. Right, it's got to be strictly less than 1 inside. What does that mean? That means 1 over f of z in absolute value is strictly less than 1 if z is less than 1, which means f of z is greater than 1 if z is less than 1 in absolute value. And this contradicts the fact that f of z equals 1 on the boundary. You can't be larger in the interior than you are on the boundary. Contradicts f of z equals 1 on the boundary of the disk. which is, z equals 1. Because by maximum modulus, if you know you're always 1 in absolute value on the boundary, you have to be strictly less than 1 in the interior. So this tells us that there must be at least one point such that f of z equals 0. Okay? So now the question becomes, there's a way to attack this which would actually show us potentially other solutions to this. But let's continue. We don't know where that point is. Where would you love that point to be? You'd love it to be 0. So this will actually, I can use this to motivate material we're going to do later in the semester. Let's have a map from the unit disk to the unit disk. And imagine here's the point z0 where it vanishes. So here, f of z0 equals 0. I want some map h such that h, let's see which way I want to go. Such that h of 0 is z0. Because if I had some map like this, and if the map is invertible, then I'll have a map h inverse in this direction. I could then imply the map h inverse and map the point z0 to the origin. And so it becomes an interesting question, when do you have maps from the unit disk to the unit disk? What do those maps look like? What do they do to the boundary? And so later in the semester, we will talk about the Riemann mapping theorem that says if you have two simply connected regions that are not the entire complex plane, then there is a map from one to the other. And so we can actually write down this map explicitly. H of z is, make sure I get this right. Let me just look it up because I will map it slightly wrong if I try to do it by. Okay, so z0 minus z over 1 minus z0 bar z. Okay. This is a little bit different notation than is in the book. This is page 219. So let's look at this function. What is h of 0? H of 0 is just z0. So this at least does what we want. It sends 0 to z0. So we need to show two more things, or a couple of more things. H maps the disk to the disk, say 1 to 1 and on to. And then if we had something like that, then this would be an isomorphism between the two. And the next thing we would want is if the absolute value of z equals 1, what do you think we want the absolute value of h of z to be? Yeah, maybe extending boundary to boundary. So let's spend a little bit of time on this. So we have the function h of z is z0 minus z over 1 minus, wow, this is just a really bad day. 1 minus z0 bar z. Oh, and that one is gone. Can someone get the piece from there? All right. So we've got h of z is z0 minus z over 1 minus z0 bar z. Thank you for not tossing it. All right. We want to show that it maps something in the unit disk to the unit disk. So could two things be mapped to the same thing? imagine h of z1 equals h of z2. Then you would have z0 minus z1 over 1 minus z0 bar z equals z0 minus z2 over 1 minus z0 bar z2. Now we're going to have to do a lot of cross multiplying and whatnot. Is this looking fun? So this allows me to talk about the importance of looking at algebra the right way. This is the most natural way to show that a function is one-to-one. Show that if 2 points are mapped to the same thing, then they're the same point. So we could now start cross multiplying. So we would get z0 minus z1, 1 minus z0 bar z2 equals z0 minus z2, 1 minus z0 bar z1. So we get a z0 on both sides from this. Then we get a z0 bar z2. We'll have a z0 bar z1. So negative z0 squared z1 minus z1. Minus and minus becomes plus z0 bar z1 z2. We'll have the same thing over there, so those will cancel, so we don't have to worry about that. Will equal minus z0 squared minus z0 squared z2 minus z2. How many solutions should this have?
Well, it's z1 times a constant equals z2 times a constant.
Right? If you fix z1, this is a linear equation in z2. Can you find a solution to this? z1 equals z2. So given that you can find a solution to it, and it's linear that has to be at most 1, then you know you're fine. That's the only solution. As linear and z1 equals z2 a solution, it's the only solution. So this shows that the map is at least 1-to-1. Now we would need to show that it's onto, that you give me any value of in the unit disk, and I can find something that's hit by it, that's sent to that. Okay. Is everybody comfortable? So we want to solve h of z equals w. W is any point in D. So we would want z0 minus z over 1 minus z0 bar times z equals w. So we get z0 minus z equals w minus z0 bar w z. So we bring the z over to the other side. We get z0 minus w. When we bring this over, it becomes 1 minus z0 bar w. And there's our z. What do we need to make sure? That it's in the unit disk. How would we make sure that this is in the unit disk? Yeah, so how would we show its magnitude is less than 1?
Isn't that just h of w? So
Ah.
So if we show the magnitude, so if we show h maps points of magnitude 1 or less than or equal to 1 to points of magnitude less than or equal to 1, we're good.
Then we would be fine. So let's just make sure we haven't done it the other way. So we would have z0 minus z over 1 minus z0 bar z equals w. So we get z0 minus z is w minus z naught w z, subtract the w, bring that, and you have 1 plus, oh, wait a minute. Oh, should this be a plus down here? That should be a plus down there. Okay. So it's unfortunately not quite the same as h of w. But that would have been a great way to do it. That's how I knew there had to be an algebra mistake, because I know the proof is a little bit longer than that. But it's very similar. Now we know z naught and w are strictly less than 1 in absolute value. The danger could be maybe z naught and w are in opposite directions. But we've got a complex conjugate over here, so maybe that will help us a little bit. So then the question becomes, what's the simplest way to calculate the magnitude of this? So we could multiply by the conjugate of the bottom and see how that goes. So we would then have the absolute value, the absolute value of z naught minus w over 1 plus z naught bar w squared. We might as well work with the magnitude squared. That would give us z naught minus w, z naught bar minus w bar over 1 plus z naught bar w, 1 plus z naught w bar. So the top becomes z naught squared. We have minus w z naught bar. We have a minus w bar z naught. And then we have a plus w squared. What do we have down below? We have 1. Now, this is going to give us a z naught squared w squared, right? And then we'll have a plus z naught bar w. We'll have a plus z naught w bar. So I can write the top as, how could you view w z naught and then w bar z naught? Mm-hmm. So I think I can write like z naught squared minus twice the real part of w bar z naught plus w squared. And then down below, I'll have 1 plus twice the real part of w bar z naught plus z naught squared w squared. And then you can begin to appreciate, that there may be a better way to do this. This is becoming a little bit algebraically intense. What's the worst case going to be for us? How could this be as large as possible? When the real part, let's do more than just the real part. W bar z naught is real and negative. That's the worst case for us. Because then we're losing nothing in the top. We're making the top as large as possible. And down here, the worst case is when w bar z, real and negative, that will make this as small as possible. So really, I think the worst possible case for us would be as if this is a real number. And then if this is a real number, we would then get z naught minus w, oh sorry, plus w squared, I think, for the top. And for the bottom, it would be 1 minus z naught w squared. And we could definitely have that. If w is, say, a positive number and z naught is a negative number, that could happen. So do you think this will always be less than 1 in absolute value?
We can eliminate the squares.
We can eliminate the squares. I'm a little bit worried about the algebra right now. Because if z naught and w are both very close to 1, the top is close to 2 or 4. And then the bottom is going to be close to 0. And so if we do something like this, we are going to have trouble. So we want this to be, so I'm just trying to say, have we made a slight algebra mistake somewhere? So we have z naught minus z equals w minus z naught bar wz. Bring this over. Oh, crap. No, it is 1 minus. Ah. All right, you got to speak up louder when you see that. All right, so it was 1 minus. All right, speak up. So if that's 1 minus, that's going to change things a lot. Then we'll have a 1 minus over here, right? Now we may go back to what was being suggested a moment ago. All right, so now that we have the minuses there, this would become, I think, a minus there. I think that's the only change. Right? And now this part is the same in both of them. And now which would you rather have, z naught squared plus w squared or 1 minus z naught squared w squared?
You mean 1 plus z naught squared?
We just need to show, this part is the same in the numerator and the denominator. If we can show 1 plus z naught squared w squared is greater than z naught squared plus w squared, we're done.
Well, 1's greater than z naught squared, and z naught squared w squared is bigger than w squared.
No, because these are less than 1 in absolute value.
Oh, yeah. So,
Right.
Okay.
So it's not necessarily. All right. So this changes the algebra ever so slightly. So now it's all down to z naught squared plus w squared versus 1 plus z naught squared w squared. So to some extent, we might as well assume everything is real now. So if you want, it's x squared plus y squared versus 1 plus x squared y squared, where absolute value of x, absolute value of y are less than 1. And so now the question is, can you prove a equality like this? We could fix an x squared and show that if you fix an x squared, what do you get? And what does this look like? There's lots of different ways of trying to do the algebra. But now that we do have the minus sign here, it is suggesting that we should just go back and show that h of z maps the disk to the disk. But it's equivalent to trying to prove this inequality.
Do you look at this sort of geometrically? So like x squared plus y squared is like the square of the hypotenuse of a triangle between x and y.
Okay.
And since that hypotenuse is contained in the disk, its length has to be less than or equal to 1.
How do we know that it's a hypotenuse in the disk?
So we're looking at x squared plus x and y.
Right.
We form like a triangle with x and y.
But if x and y are both really close to 1, the hypotenuse will be greater than 1.
Oh, yeah.
So unfortunately, we can't quite do that. One thing is try to look at like geometric means, arithmetic means, something like that. Do we have a relationship between x squared plus y squared and x squared times y squared? And try to do something like that and then put in the 1. But I think it's better to just go back and look and see what do we do to w. But given that if this is supposed to map, this equality should work. And so we should be able to prove that directly. So let's look at now h of w is z0 minus w over 1 minus z0 bar w. And so we just want to show that this is in the unit disk. So I think this might be exactly the same calculation we were just doing a moment ago. So is there a better way of doing this? I think the book does it with an r e to the I theta. Let me just double check. This was page 219. Oh, wait a minute. Do they do it by maximum modulus? Yeah, it's a maximum modulus argument. Now I remember. I knew that we didn't want to look at it that way. What we were trying to do is we were trying to show that if w is less than 1 in absolute value, that we're hit. All we need to do is show that this is in the unit disk and we win. So let's look and see what happens when we put in w has absolute value 1. So assume w equals 1 e to the I theta. And then if we can show that the absolute value is 1, by the maximum modulus principle, it'll be strictly less than 1 inside, and it will map the unit disk to the unit disk. And we've just shown it's 1 to 1. So this gives you some sense of the power of the maximum modulus. I was trying to do the algebra, and we're down to something like this. We could probably make that work. But now if we try this, then h of e to the I theta is z0 minus e to the I theta over 1 minus z0 bar e to the I theta. Well, when we go through and do all of our algebra over here, that's just taking the case w equals 1. So this yields, after the same amount of algebra, z0 squared plus 1 versus 1 plus z0 squared times 1, which is true. So has absolute value 1. So h of e to the I theta in absolute value is 1. So that's a much better proof than trying to do the algebra, though I think this would work. We just show that on the boundary of the disk, it has absolute value 1, therefore it's strictly less than 1 inside. We have the onto, we have the 1 to 1. What this also tells us is that our initial list was incomplete. When we said z squared, z cubed, these were the only ones we could think of. Here's another one. Z dot minus z over 1 minus z naught bar z. Something like this works. Maybe what we can do is, going back to the original problem that inspired all of this, is we can come back over here. We showed that f of z equals 0 has a root. We could apply this transformation and move that root to 0. And now that that root is at 0, we have a function which is 0 at 0 and has absolute value 1 on the boundary. Must that now be of the form z to the n? So maybe the original function didn't have to be of the form z to the n, but after we do a simple transformation like this, maybe that has to be of the form z to the n. So there's a lot of really good stuff in this, and this is putting material in the bank for later in the semester when we start getting to the Riemann mapping theorem, and you get a sense of why you care about these. Why do we care about automorphisms? You're mapping the space to itself. Well, if we can map the disk to itself, we can move the action to whatever point we want in a harmless way. it's going to just shuffle things around inside, and it's going to keep boundary to boundary. All right, so long digression. Going back to the original thing, the claim was it's enough to show f of z equals 0 has a root. We've shown f of z equals 0 has a root. We did it by looking at the function 1 over f. We assumed that there was no root. 1 over f then was equal to 1 on the boundary. So that implied that absolute value of f was greater than 1 in the interior, which contradicted this. So we know that f of z equals 0 has a root. All right. Now what we want to do is we want to show that f of z equals w naught has a solution. We know that f of z equals 0 has a solution. So no, f of z equals 0 for some z naught. So f of z naught equals 0. Solve f of z equals w naught in the disk, in the unit disk. And we know also that the absolute value of f is 1 if the absolute value of z equals 1. Okay, so how would we try to show now that there is a root to f of z equals w naught? But if we're going to use Rouchet, we want, say, a of z is greater than b of z if z equals 1. Then if a has a root, so does a plus b, right? So what would we choose for our functions? So a would be f. All right, so let's try a of z equals f of z. And you want to try b of z is negative w naught. And now if you look, is the absolute value of f strictly greater than the absolute value of b? Yes. Therefore, f of z minus w naught has a root. And this is the nice thing, is because we know the absolute value of f is 1 on the boundary, it's got to be larger than the absolute value of negative w naught. And so now we have a solution everywhere. Okay. So a lot of good stuff in this problem. It uses max modulus, it uses Rouchet. It also allows us to talk about mapping a space to a space and seeing why we care about something like that. I think we've still got about 10 minutes. If nobody has any preferences, I think the Taylor series one with the z to the minus 5 and z to the minus 2 was a nice one. Do people want to see that one, or? So a lot of it, it's similar to this. It's trying to find the best way through the algebra. So f of z was, I think, a minus 5, z to the minus 5 plus a minus 4, z minus 4. And g of z was b minus 2, z minus 2 plus b minus 1, z minus 1. And the question is, what is the residue at z equals 0 of, it was f of z over g of z? All right. Well, if we look at f of z over g of z, whenever you have expressions like this, you always want to pull out the first term. So we'll pull out an a to the negative 5, z to the negative 5. And then we'll be left with 1 plus a to the negative 4, a negative 5z, plus dot, dot, dot. And we'll assume that a to the minus 5 is not 0 when we're writing it like this. And then we'll pull out over here b to the minus 2, z to the minus 2, 1 plus b to the minus 1 over b minus 2. So what do we get? We get 1 over z cubed from this. We get a minus 5 over b minus 2. And then we have this expression 1 plus, I'll call this alpha minus 4. I'll just call it alpha 1 z plus alpha 2 z squared plus dot 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 over 1 plus beta 1 z plus beta 2 z squared, where the alphas and betas are easily determined in terms of the a's and b's. And this whole function here, let's call that h of z. What do we know about this function at 0? What does it equal? 1. And it's a holomorphic function. It's going to have no poles as long as z is sufficiently small, because the series converges. So if we want to figure out what is the residue, all we need to do is we need to just figure out the z squared term of that. Because h of z is going to be h0, well, we'll do I guess this way. H of 0 plus h prime of 0z plus h double prime of 0 over 2 factorial z squared. And then because I have a 1 over z cubed, all that really matters is h double prime of 0 over 2. So to finish the problem, we just have to take the second derivative of this. Oh boy, right? We have a ratio of two functions. What rule do we get to use? And the only thing better than the quotient rule once, or I guess the next thing better than the quotient rule once, is the quotient rule twice, right? So you could do this using the quotient rule twice. There's a way to avoid using the quotient rule. Who would like to see how to avoid the quotient rule? Okay, so here's how you avoid the quotient rule. I was thinking about this as I was walking in today. When I look at the numerator here, if I'm using the quotient rule, I don't care about any terms beyond z to the 4th. Because when I take two derivatives, it's still going to give me at least a z cubed. Down here, I don't care about anything again beyond z to the 4th. So if I want to, I could actually truncate these at z to the 4th. It's still a little bit painful. Over here now, what I'm going to do is I'm going to expand out the denominator. So 1 plus beta 1z plus beta 2z squared plus beta 3z cubed plus dot dot dot. We have that to the negative 1. This is the same as 1 plus beta 1z plus beta 2z squared plus dot 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 inverse. How should I expand 1 plus something inverse?
How did you get from that to that?
From this to this?
Oh, no, never mind.
Yes.
Never mind. Yes.
Isn't this much better than taking quotient rule twice? I used geometric series. So this is going to be 1 plus beta 1z plus beta 2z squared plus dot dot dot. Now, actually, I should write this as minus minus, right? So the first term should be minus, right? Because when you do a geometric series, it should be 1 minus r. So I need to do a minus minus. Then the next term will be plus beta 1 z plus beta 2 z squared plus dot 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 squared. Do I have to worry about what comes next? No. Why not?
Because it's all going to go away just like, because it's z cubed.
Yeah, I have a z cubed down here. I only care about this up to the z squared term. So over here, the nice thing is because all of the terms here have at least a z, All the terms here will have at least a z squared. All the terms here will have at least a z cubed. I don't need to worry about that. When I expand the square of this, do I need to worry about the beta 2z squared? No, because that'll be a fourth power. Do I need to worry about the cross term? No. So when I expand this out, I'm going to get 1 minus beta 1z minus beta 2z squared. Do I care about anything else from here? Plus, then when I square this, I'll get a beta 1 squared z squared. And I don't care about anything else. So now when I'm trying to understand h of z is now going to be 1 plus alpha 1z plus alpha 2z squared plus dot 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 times 1 minus beta 1z minus beta 2z squared plus beta 1 squared z squared plus dot dot dot. And now all I need to do is find the z squared terms. So it's going to be something, which is the constant term. Right, the constant term is not that bad, plus something z. And now let's find the z squared term. So the z squared term, the 1 can hit the z squared, right? So I could have a alpha 2. I could have the z's hitting the alpha 1z term, right? So it'll be minus alpha 1 beta 1 minus alpha 1. Oh, wait, that's a z, not a z squared, right? Oh, no, no, no. That's a z squared. OK, so it's just. Right. So the 1 hits the z squared, and the 1 won't contribute anything else. The beta 1z, the only thing it can hit is the alpha 1z. So it'll be alpha 1 beta 1. The minus beta 2z squared can hit the 1. And so we get a minus beta 2. And then the plus beta 1z squared could hit the 1. So
and
plus.
You need a z after the alpha 1 beta 1, I think. Just before.
I'm sorry?
Oh, never mind.
OK.
Never mind.
OK. And then that will be the z squared term. So the solution is just going to be a to the minus 5 over b to the minus 2. Alpha to the minus alpha 2 was, I think, a minus 3 over a minus 5 minus alpha 1, which is, I think, a minus 4 over a minus 5. Beta 1 is b minus 1 over b minus 2. And then plus. Wait, that was the beta. Oh, no, I was doing this too. I'm going to just leave it as the alphas, because otherwise I'm going to screw it up right now if I just try to do it. A minus 5, b minus 2, alpha 2 minus alpha 1 beta 1 minus beta 2 plus beta 1 squared. And I think that's much better than doing the quotient rule twice. So a lot of this is trying to find good ways to do the algebra. The best way to find good ways to do algebra is to do bad ways and really hate it. And then say, OK, I got to find a better way to do this. I don't remember how I actually wrote out the solution to this problem. And did I do it this way, or do I do it with the quotient rule twice? The quotient rule twice isn't too bad. And if you make the argument that it's enough to just chop things off at z to the 4th in each one, it's not terrible. But you've still got to do the quotient rule twice. If you needed to do that, you should have done the calculation with Mathematica. It's a Calc 1 problem. It's a tedious Calc 1 problem. Right? So Mathematica has symbolic differentiation. You can write down a finite polynomial, take the derivative of their ratio, do it again, and then set it equal to 0. So you should look and learn how to do something like that with Mathematica. All right, so I will have you watch the video, but every now and then I do want to flip a few classes just because I think it would be useful to just really stop and do a lot of problems like this in great detail. In a graduate class, you're not going to be able to do this. They're going to keep working and moving at warp speed. And what often happens is you learn the theory, but you don't learn how to apply it. So we have the opportunity to use the lectures from the past, and I want to do that now and then. All right. Have a good reading.